All right, well, welcome to week 5. We're moving forward, and we're going to start sinking our teeth into chapters 3 and 4. And as I mentioned last week, I just want to kind of skim over parts of chapter 3. So chapter 3 is all about synthesis applications. So the topics in chapter 3 are additive synthesis, modulation synthesis, focusing particularly on FM synthesis or frequency modulation, wavetable synthesis, subtractive synthesis and filters, modal synthesis, which is using synthesis to recreate the harmonic modes of a vibrating object. There's a companion code where I just use sine waves to produce an orchestral triangle sound, and distortion techniques. And there's a companion code at the very end of chapter 3, which synthesizes, does sort of a basic approach to synthesizing kick, snare, hi-hat sounds. So there's lots of little things in there. Probably the most useful application of chapter 3 is as you get towards the end of the semester and you're thinking about your final projects, you might want to come back to chapter 3 just to sort of get some ideas, try some things out. So there are two things in chapter 3 that I want to cover before we look at chapter 4. That's going to be the focus of what we do over the next couple of weeks, chapter 4. And the homework will be based on chapter 4, parts 1, 2, and 3, basically, 4.1, 4.2, 4.3. So what I'm going to do in chapter 3 is talk about filters briefly and talk about range mapping and range manipulation, which is part of the distortion chapter, signal distortion techniques. But both of these things, filters and range mapping, these are really useful techniques that will come up in a variety of circumstances. So we'll see how far we get. So I've got the server booted here. I'm going to boot it again just to make sure I'm using the right devices. Okay, so if you've ever taken an electroacoustic music course and talked about filters, you've probably been taught that there are 4 basic types. Low-pass filter, which is LPF, high-pass filter, HPF, band-pass filter, BPF, and band-reject filter. So the low-pass will pass low frequencies and attenuate high frequencies. The high-pass does the opposite. The band-pass will pass a band of frequencies but reject things on the outside of the band. And the band-reject filter does the opposite. It's also called a notch filter. So yeah, let's just see how these are implemented very quickly. So I'm going to cook up a very basic UGen function. So we'll make some moderate level pink noise. And so this is just going to sound like this. Normal, regular pink noise. So the low-pass filter takes 2 parameters, the input signal, which is going to be sig, and a cutoff frequency, which defaults to 440, but you can set it to whatever you like. So here's 2000, here's 1000, 500, and 200. So you can hear very clearly it's passing the low frequencies, and the lower the cutoff frequency, there's a smaller and smaller part of the audible spectrum that gets preserved. High-pass filter, kind of the same thing. If we set this to 200, we're going to be passing most of the spectrum and just rejecting the bottom chunk. Here's 1000, 4000. And of course, this is totally modulatable. So if we say mouse x.kr, this is a unit generator which takes the horizontal mouse position on the screen and will map it between a minimum and a maximum. So let's say 100 to 2000. And we'll poll the values. Polling this is at the very end of chapter 2. It's a method which can be applied to a UGen which will print the output values of the UGen to which it is applied in the post window. I mean, it's not going to post every single sample value because that would be a ton of numbers. It just posts, I think, by default once every 10 times a second. So it's sort of just enough to see what we're working with. So here we go. Right, you can also do a You could do a sine wave here. So we'll say dot range 100 to 1,000, or let's do 100 to 2,000, right? And anyway, so you get the idea, right? We can modulate parameters of a filter just like we can modulate other aspects of other UGens. And the most important thing to convey with regard to filters is that they almost all of the filter UGens in SuperCollider are volatile, in that if you feed them bad numbers, they will explode in your face. This is just the nature of how filters work. To design a digital filter that emphasizes or does something special with the spectrum, there has to be some sort of recursion in the algorithm. And when there's recursion, there's always a risk of explosive feedback. So a good sort of min and max to always work within for any sort of cutoff or any sort of frequency parameter for a filter is to never set it lower than 20 and never set it higher than the Nyquist frequency, or to be even safer, you can just set it to 20,000 or less. If, depending on the filter, all filters are designed differently, if the cutoff frequency or center frequency is too high or too close to zero, and certainly if it's negative, you'll get something really crazy. So I'm going to give you a demonstration. I'm not going to play it, but what we'll do is go back to the low-pass filter, and we'll do mouse x.kr 100 to 1,000. So this is fine. Make this a little bit higher. So left edge of my screen, it's 100, and so we're well in the safe zone. One way this can blow up in your face, even if your values are fine, is if you're using a second monitor and it's to the left of your current monitor. I believe like if your mouse goes off this screen and onto the next screen, it'll keep going down, because I think by default these numbers are not bounded. It'll just keep extrapolating from your min and max. So fun surprise there, right? What I'm going to do here is say play this out to bus 4. So now we're not going to hear anything, but if we do show scope, so you can see there's nothing on our output buses, but if I show 6 instead of 2 channels, now we're looking at some more audio buses. The lowest 2 are output, nothing is playing right now. 2 and 3, so 1 and 2 are output, 2 and 3 are input, so this is my voice on 2, and I have nothing plugged into my other mic input. And then here's the filtered noise here. So I'm going to increase, so we can see, let's go all the way up to 10,000 here. So there you go. So there's largely unfiltered pink noise, and then you can see a lot of the high frequency energy goes away when the mouse is at the left. So this is fine. So I'm going to set this now to be negative 100. Okay. And watch what happens with our signal as we get, let's poll it. And so you can see the numbers in the post window. And right as we start to dip into 0, this happens. Yeah. So they're really dangerous UGens. They shouldn't be, there's the blessing and the curse. The nice thing and the terrible thing about SuperCollider is that there are no guardrails. There's no, there's no boundaries. There's nothing to stop you from falling off a cliff, So, you have a lot of flexibility to do all sorts of interesting things. And people do this intentionally with like heavy limiting and compression and stuff in order to get crazy distortion effects. But yeah, if you're not, I've made a recording of this with my mixer muting the channels. I think it's this one. Yeah. So that's what it looks like, and it looks clipped, but there's like different versions of SuperCollider and different versions of Mac OS with core audio that do different things. But if we just grab this chunk here, let's do the whole thing. We're just going to de-amplify this, like turn it down by 20 decibels again and again and again and again. So they're big numbers. These are really, really, really big numbers. And I think as of SuperCollider 3.12 or something like that, there is a server attribute which will clip the values leaving the server and going to core audio. I think Windows and Linux do this automatically, but Mac is like the dangerous one because it just lets you... Anyway, you get the idea. I won't harp on it too much. Filters are dangerous. So any frequency parameters should be bounded within the audible spectrum. And if you're ever unsure of the sound that's about to be produced, then really what I recommend is just muting your system volume or something like that, taking your headphones off, muting some mixer channel, and there's I think on Nathan Ho's blog that I showed, he also has a post like tips for beginners, and like the first thing is level safety. So lots of good resources there. There's two other filters that I find myself using a lot. Let's go back here again. I don't know, 6,000 or something. One is the Resonant low-pass filter, RLPF. This one takes a third parameter called RQ, which is short for reciprocal quality. And RQ is another potentially explosive parameter in that it should always be greater than 0. And I think it can be a little bit greater than 1, but my practice is to make it less than or equal to 1 and greater than 0. And it's a measure of how much resonance there will be at the cutoff frequency. There's a very small amount of resonance at an RQ of 1. And as you approach 0, resonance increases in a reciprocal fashion. So a good way to visualize this is to let's set the let's do the vertical mouse position will control the quality, the reciprocal quality, and the horizontal position will control the cutoff frequency. And we will open up the Freakscope, which is a spectrum analyzer. And okay, so you can see at the top of the screen, the RQ is close to 1. So it kind of behaves a lot like a regular low-pass filter. But as we reduce the reciprocal quality value so it gets closer to 0, you'll see resonance emerge at the cutoff frequency. Yeah, classic wind sound, right? Yeah. So, and then there's a resonant high-pass filter, which is the same thing, but high-pass filter. And then very briefly, I'll also show band pass filter, which, like the resonant high-pass and resonant low-pass, also has a reciprocal quality parameter, same idea. In like textbooks and things like that, the quality of a filter is usually just starts at 1 and goes up to infinity. And in SuperCollider, it's represented as the reciprocal of that value. And it's done that way because my understanding is that it saves a calculation on the server and is slightly more efficient for the user to just do the math as they enter the value. So it's the same idea. So with a bandpass filter, the closer we get to 0, the narrower the band. And again, you don't want to ever be at 0, and you don't want to go too high above 1. Can bring this up a little bit, I guess. And this just a common feature of any filter which removes a lot of content from the spectrum is that you're just taking away a lot of energy from that signal. And so as a result, you may find yourself wanting to compensate for the loss of amplitude. So with something like this, it's, if your RQ is, for example, at 0.1, kind of fixed there, this is always going to be a pretty quiet signal. It's peaking at like minus 35 or something. So it's not unreasonable to do something like just increasing by some amount of decibels.
You have to compensate the energy loss.
Yeah, it's kind of, this is kind of context specific because, for example, if you're working with an audio file, the spectrum is going to change over time, and sometimes it will have a lot of energy at the center frequency, other times not. So this is really just kind of a creative decision you have to make. It's just level management, basically. Just recognizing that filters remove a lot of energy and therefore will drop the amplitude of the signal coming out, and then you may need to make up for that loss in some way. Okay, so that's all clear enough, filters? These 6 will get you pretty far. There's a lot more. You can browse UGens filters, and there's others, but I find that these 6 tend to be kind of, will get you, anyway, go nuts. Go have a look and go through the help files and play around if you like, but just, do be careful. Because filters play dirty. All right. Probably should have been copying and pasting this as I went, but I'll add some more later. Let me talk about range mapping. And to begin, I'm going to create an array of numbers. And I'm going to plot those numbers. So I'm just plotting the numbers 1 through 100. We can look at this. I can push M to change the plot style, however you want to visualize this data. And we're going to work with numbers first, then we'll apply this to signals. So let's say, I think what we're going to do is make an array containing this first array, and then a version of this where we say linexp. Linexp is a method that operates on numbers, arrays of numbers, and also signals. And it will take the value of whatever it's applied to and map it from a linear range from A to B onto an exponential range from C to D. So in this case, our starting range is 1 to 100. Just, again, this is just the numbers 1 through 100, the integers 1 through 100. So say 1, 100. These are the min and max of the starting range. And then we'll want to map these onto, let's say, the same range, but it's going to be exponential. So if we plot this, I think this will work. Yeah. You can see how it has bent the data. So the range of the input and the output is the same, but this is what linexp will do to a number. Let me give you an even simpler example with just a number. Let's say, let's say we have the numbers, 1 through 20. We just pick a random number 1 through 20, and we want to map that onto a frequency between 40 hertz and 1,000 hertz, or something like that, right? So pick a random number from 1 to 20, and we'll map that from 1 to 20 onto 40 to 1,000. Like this is something that we really can't do in our heads. Maybe if we were going from a linear range to another linear range, we can kind of do the math mentally. But basically, we're going to get some random number and then map it. So we picked 5. And if we take the starting range, project it onto this range, and apply an exponential curving, then 5 becomes the number 78 point, etc. Does this make sense? This comes in handy whenever you're working with numbers that exist on a linear scale, and you want to then apply that data to some other parameter that requires a different range. This can be really useful. We can bend these numbers the other way by saying explin. So this third version here treats the starting range. The starting range is at the beginning, as if these existed in an exponential context, and tries to linearize them. So the result is it makes this logarithmic curve here. And you can also do linlin. This is also like just mapping from 1 to 20 onto, let's say, 300 to 400. Just picking these numbers randomly. So this picks a random number from 1 to 20, which is 16. So it's sort of near the top end of that starting range. And if we just project that range linearly from one to the other, it becomes this number, right, which is proportionally the same amount of distance between A and B. And as I'm saying this, I know it sounds pretty abstract, like we're just juggling numbers here. So there's 2 more which are useful. Okay, so let's do lincurve. I guess really we only just need this one here. 1, 100, 1, 100, and then we provide a curve value for lincurve. And it's the same behavior as we've seen in envelopes, where 0 is linear. So if we said 0 here, this bottom one is exactly the same because we haven't actually curved this at all. But positive values will curve it one way. Right? So this is with lincurve 8. And this is with lincurve -8. Right, so this is the starting at the beginning, linexp, explin, and then this is lincurve, +8, lincurve, -8. So we have lots of flexibility. Now, let me show you how this is interesting with signals. Let's say 400, 402. We'll open up the scope. Try to make this look nice. And let's say sig equals sig.lincurve. Right, so we're taking the actual sample values of this audio signal, which, well, let's get rid of this mul2 here and put it at the end. So a sine wave, most oscillators are going to range from either 0 to 1 or -1 to 1. And sine wave is, sine osc is bipolar. So the starting range is -1 to 1. And we want to map it onto the same range, but we're going to curve those values as we do. So let's just make this a value of 1. So it's going to curve them ever so slightly in the exponential direction. Oh, I forgot a semicolon. So you can hear the timbre has changed, the shape of the waveform has changed, and the spectrum has also changed. We've introduced some harmonics just by pushing the waveform, sort of like Play-Doh, like clay, sort of mushing it around a little bit. So one thing that we can do here is say mouse x.kr, and we'll say 0 to 5. So we're going to use the mouse to dynamically curve the waveform. We'll start on the left here. So that's just sort of a very inexpensive way to take a plain oscillator and then start doing interesting things to it. Something else we could do is let's just make another variable called mod, and this will be an interpolating noise generator with 2 unique channels, ranging from -3 to +3. So we're getting 2 modulators. Because we're expanding multi-channel, we're turning this one into an array of two ones, so we'll get two unique noise generators, one operating on the left channel, one operating on the right channel. Let me make this a little bit more extreme. And then we might, I don't know, add another one. Let's go. Tantalizing. We'll just play around here for the rest of class. We've just been making these sort of individual functions, but let's not overlook the fact that we can make a bunch of different synth defs and then make a bunch of synths and add envelopes and fade them in and out and do all sorts of interesting things. Just takes a bit of time to build it all, but we can get some really nice results. One rule before we move on to chapter 4 is that with any of these exp range mapping methods, like if we say, let's see, we want to pick a random number from -10 to +10. This won't work. Well, it doesn't give us an error message, but it gives us not a number, which is what NaN means. If we were to do linlin, well, yeah, this is fine. I mean, this won't do anything because we're putting it onto the same range. But what I'm trying to say here is, if you use linexp or exprange or exprand or any sort of exponential number generating method, the target range, the exponential range, can't include or cross 0. So for example, we can take this range, this random number between -10 and 10, and map it between 1 and 100. That's fine, right? 1 and 200, right? We're just taking random numbers between -10 and 10 and just putting them onto this range. And we can also do a negative range. I think this is fine also. But we can't map it onto a range that includes 0 or crosses 0. I mean, so it'll, I think it works if it picks. I'm not sure why it's not always failing here. But same thing with rrand and exprand. Like, this is fine. Exprand, this is not fine. Right? So this, yeah, just something to watch out for. Right. And there was one more thing I wanted to mention here. Just make one more simple function here. Say we'll do the binaural beating again. If we, well, here's what we're going to do. If we say LF try, and I think I've definitely shown the range method from time to time, right? So if we say range 50 to 800, slow it down a little bit. So something like this. I'm going to set the phase to be starting at the beginning. Make this a little bit clearer. And if you listen with perceptual ears, it sounds like it just barely spends any time in the lower pitch and spends most of its time in the higher pitch. And that's because we're using a linear oscillator to modulate the frequency. This LF tri is just a straight line going up, straight line going down. And this is, we have a logarithmic perception of frequency because we think of octaves as being linearly spaced, but the frequency doubles each time. So this is another good example where it makes sense to map these values from a linear range to an exponential one. And we can do that by saying linexp 50, 1200, 50, 1200. And this should sound to your ears like a more uniform trajectory across our perception of pitch. But there's an even faster way to do this, though. We don't have to say linexp. We can just say exp range instead of range. And this produces the same result, but we don't have to type quite as much. Yeah. All right. There's also two other range methods. One is unipolar. If you go to the UGen help file, you can see we instead of saying dot range min max, we say dot unipolar n, and the range will be from 0 to n. And bipolar, we say bipolar n, and the range will be from negative n to positive n. So you can UGen help file is a good. There's also curve range. It's a good place for just looking at different range options. It's a good place for methods which are applicable to all sorts of different UGens. Can be helpful. So I really would be delighted if you'd read chapter 3 with at least sort of some attention to detail, because I think you'll find some interesting things in there. But for now, unless there are any questions, I'm going to move on to chapter 4. Any questions? Okay. Great. So chapter 4 is all about sampling. And what that means in this context is we're working with creative, generative sound processes that involve audio files. And so we read those audio files into memory on the server and then play them forwards, backwards, fast, slow, and all that sort of thing. So the first thing we want to do is get some sound files loaded into buffer objects. So a buffer is a block of memory we can allocate, which a buffer object lives on the server, so we can't really do anything with buffers unless the server is booted. And the simplest way to do that, to load a file into a buffer, is to make a variable, and we say Buffer.read. And we provide the server onto which the buffer should be read. So this is lowercase s for the default localhost server. And then the path, the file path to that folder. And my favorite, I've got a couple of folders here, files here, just some sounds here. And then some drums. Me talking about sound breaking my brain.
It just completely broke my brain. I had no idea what I was hearing or that sounds like this could exist.
Okay, so let's do the pipe. So I'm going to click and drag this one. Click and drag it right here. I think you can also do copy and paste, like if I click here. I don't want to play that, thank you. Yeah, if we just copy and paste, like we were just copying and pasting in a text editor, we get the same sort of thing. So this is the quickest and simplest way to get sound and to test that it worked. After you read that file into a buffer, you can just say b.play, just to confirm that it works. So that's good. Buffers have attributes that are populated once the buffer reading process finishes. So if we say b.query, we'll get some information returned to us in the post window. Whenever we allocate a buffer, it is automatically given a buff num by the server, which is an integer a unique integer that identifies that buffer. So we can refer to buffers with their buffnum or using the language side variable we've created. This is the number of frames in the buffer. This is the number of channels, so it's a monophonic buffer, and this is the sample rate at which the file was recorded and created. Frames are like samples. They're not exactly the same thing. But if we have a one-channel buffer, right, this is just the beginning and the end, and it's just, numbers. Just basically think of it as just a sequence of numbers representing the waveform. So if we have a stereo buffer, right, so two channels, but same number of samples in each one, this is a channel. This is a sample. And this is a frame. And think of it as like a movie, but it plays on two screens simultaneously. You can have a frame, which includes, two images or something like that. So in the case of a stereo buffer, right, if we have a mono file and a stereo file that are the same length, they have the same number of frames, but the stereo one has twice as many samples. Is that clear? Just some terminology. Nothing too important. So other methods, b.duration gives us the length of the file. A bunch of these are also obtainable just with the methods that are shown in the post window. We can get the buffnum, the number of frames, just basic information. These are language side methods. Sometimes we want this information on the server, and there are UGens. For example, buff.dur is the unit generator equivalent of .duration. Let's see, buff frames is this one. Buff. There's a couple other ones, but anyway, this is all I'm really showing here is that you can extract information from a file once it's been loaded into a buffer. The biggest problem with this approach is that if I send this code to you, even if I also send you the audio file, you're going to have to change this path because it's just not going to be the same path because this is specific to my computer. So what we're going to do here is I'm going to save this on the desktop. Okay, so here I have my code file and my project audio files. I'm going to close this briefly. And here I'm just going to create a new folder that contains all of these things. We'll call it week 5 project or something like that, right? So now I have everything contained in a folder. We're going to open up this file again. And there's a special keyword called thisProcess, which is a way of essentially referencing the interactive environment in which your code is being run. So just if you run this process, it just says a main. And okay, that's not very meaningful, but there are a bunch of methods that are available for this process. One of which is nowExecutingPath. And if you run this expression in a SuperCollider code file in the IDE, which has been saved somewhere on your computer, it will return the absolute path to this file. That's what you're seeing in the post window. And this we can use to our advantage because we know that our audio files are stored in the same location. So here's what I usually do here. I use a class called PathName. PathName takes a path and returns a path name object that represents that path location. So we haven't really done anything here other than we're just, like this here is a string. It just returns a plain old string, which is this string here. We don't see the quote marks in the post window, but it's still a string. And then this version is a path name, but it represents the same thing. And once we have a path name, we can say dot parent path, and this returns a string that points to the folder that contains this code file. And then we can say plus plus, what was it, pipe dot, forget if it's wave or AIF, wave. Right, so now, what we've done here, if we evaluate this line, is we dynamically generate the exact path to this file. And the only thing we need to make sure we do is just never mess around with the contents of this folder. So even if we move this folder somewhere else on my computer, or I turn it into a zip file, send it to you, and you unzip it, everything is in the same relative location. And so this code will always point to that file. So now we can say something like, let's free all the buffers. Actually, we can just do b.free, right? Because b is still alive. We can say free, and then it's gone. And so freeing a buffer says to the server, you don't need this anymore, free up that memory for other things. So if you were to keep running this file again and again and again, you would just load the same file into another buffer, and then another buffer, and then another buffer, and eventually you'd run out of buffers, and you'd get some warning or error message or something like that. So it's good to be tidy with your workspace, and when you're done working with buffers, free them. And you can also do buffer.freeAll, which is just wipes all the buffers away.
What is the maximum buffer?
The maximum number of buffers can be obtained with s.options.max, I think num buffers, is that right? 1024. Yeah. And you can change this if you want, but let me know if 1024 is not enough for you, and then we'll talk. I think every now and then I've had projects with like 500-600 buffers or something like that, but I've never had to change this value. So, okay, so with this here, now we can say, well, we could even say like path equals this, and then b equals buffer.read s path. Right, so there we go. So we have our clever expression, which dynamically generates exactly the right path, assuming that the file is in the same location as the code file, and then we read it into a buffer. And there we go. We're good. So this is what I refer to as the thisProcess.nowExecutingPath method of reading buffers. And you should always do this. I don't always do it because sometimes I'm just doing an off-the-cuff demonstration and I know I'm just going to discard the code immediately after. But whenever you're working on a large-scale project, or you're submitting something or sharing code, you should always use the thisProcess.nowExecutingPath method. With the time we have left, I want to introduce, see if we can introduce both of the buffer playing UGens. The first is PlayBuff. And PlayBuff has a good chunk of arguments, but you don't need to provide all of them. First is the number of channels. As I think I mentioned either last week or the week before, when you build and play a UGen function, the channel size of everything inside of it needs to be fixed. So this parameter, num channels, cannot be modulated. You can't use an argument to control it. You have to basically announce upfront the number of channels in this PlayBuff. So it's basically going to be only capable of playing mono files or stereo files, or you know, I guess if you're working with crazy multi-channel files, then that would be the case there. You know, there are ways to make a synth-def be able to handle both types, but there's always some sort of like workaround which I don't really, you know, I never find myself needing to deal with. So we could do this. This would be fine because this just returns the number of channels in that buffer. But we could also just put a 1 here. Next is the buffnum. And again, we can do b.buffnum. And we know this to be 0, so we could put 0. But what we'd be doing here is making it so that this UGen function is always going to play this buffer. If we have like 20 different buffers loaded, we might want to make an argument for this. So we would do something like this, maybe. I think we could even do this. Just default it to b.buffnum. What I usually do is just this. I mean, if we're doing a quick and dirty example here, like not building a synth-def, not something which is going to play many different buffers, you know, it's really up to you. There's rate, which is the playback rate. We'll come back to this. Trigger and start position we'll come back to. Loop 1 if you want playback to loop when it gets to the end, and 0 if you don't. And then at the very end is our good friend done action, which you will remember from envelopes. PlayBuff, like UGen, has an end. When it gets to the end of the buffer, if loop is not 1, if loop is 0, PlayBuff will check its done action and do whatever we want it to do. So if we ignore this and play, we see we create a synth, and at some point the file ends, but this never goes away. So we'll hit command period, and instead we'll say done action done.freeself, and now it disappears when it gets to the end of the file. So this is the simplest version. Something you might notice here is if we play it here and here, 2 different pitches. Very strange, yeah? Why would it do that? The reason is because my server is running at 48,000, but this file was recorded at 44.1. Now like a lot of like DAWs and stuff, if you are working at a project sample rate of one thing and you drop a file that has a different sample rate, it'll usually warn you. It'll say, hey, I noticed this file has a different sample rate. Do you want me to resample the file or change the project sampling rate? Because you really have to do one or the other, otherwise everything plays back at the wrong pitch. And just to visualize what that looks like, let's see, if we have, you know, we have our sample clock here, which this is like the server is just counting samples, and it's like doing, you know, 48,000 samples per second. And then if over here we have our buffer sample rate, you know, whatever, if that's like 44.1, then it looks like this, like the samples are not as densely packed together. And if you just feed this file to a buffer playing unit generator, then it's going to just try to line up the samples, and you can see it just kind of ends up, you know, resampling it, and which as a result has to line the samples up with the sample clock, and so it'll just play faster or slower depending on the mismatch. So the way we fix that is with the rate argument. I mean, the value we want is, let's see, this is, right, this is too high, so it would be, I think, 44.1 divided by 4800. Right, there we go. So we just need to compensate, but this is annoying. We don't want to have to do this ourselves. There's a unit generator called Buffer.read, which will, you give it a buffer, and it will extract the buffer sampling rate, and it also knows the server sampling rate, and it does the math for us. Right? So that's good. And this play method is a convenience method that automatically does the rate, the buff rate scale thing. Right? So now we're good. And rate is, I mean, so this is really just to match the sampling rates of the buffer and the server, then we can do all sorts of fun things, like if we drop it by 0.5, goes down an octave. If you don't want to think in terms of ratios, you can say MIDI ratio. You give it a semitones value, and it will convert that to the appropriate ratio, which in this case is 0.5. Right. You can do right, or we can do, floats, microtonal versions. Yeah. Yeah. So I think, well, we're sort of out of time, so I do want to give a quick demonstration next week of trigger and start position and loop and how those can provide more creative options. And then next week I'll also introduce Buffer.read, which is the other buffer reading unit generator. It has the same function, but the design is different, so it lends itself towards some applications a little bit more easily than PlayBuff. But they're both good choices, and so I think that's a good place to stop. Chapters 3 and 4 are in the library. Homework 3 is assigned. It'll be due in 2 weeks, and I think that's about it. So again, I suggest looking at the homework early.
Tonight.
Yeah, just look at it, right? Look, and just to get a sense of what you'll be doing. We have more to talk about, so if you don't feel like you can complete it in this first week, that's fine. But it just get the wheels turning, basically. All right, very good. I will see you all next week.